Hello everyone, WABYA here. I thought we'd make a short video and have some fun using the Siglent spectrum analyzer. Still using my trustworthy 3021X. Still madly in love with it. And I thought what we'd do is use it to characterize the transmitter characteristics of a typical ham radio rig. In this case I'm going to use my Flex 5000, which is a software defined radio. So I get a lot of questions, people wondering how they can characterize or determine if their signal is clean, how wide is their signal, are there distortion products, harmonics, things like that. And those things can be answered very, very quickly and accurately using the spectrum analyzer. So what I've done is let the spectrum analyzer and the radio warm up for about 10 or 15 minutes. Got a D104 connected up to the front of the Flex. I've got Power SDR, which is the control software for the Flex, up and running. I'm just going to use a arbitrary frequency. I picked 20 meter band 14.2. We'll be using the upper sideband mode, and that's going to be our test signal for characterizing the radio. So let's just assume that you wanted to know how wide your signal was when you're, say, using sideband, upper sideband, and you didn't have any other equipment other than a stock spectrum analyzer like the 3021. It's pretty easy to do, and I'll show you several ways to do this. The first thing we want to do is make sure that the radio isn't going to damage the spectrum analyzer front end. The spectrum analyzer front end is very, very sensitive. You want to make sure that you don't overload it with too much RF energy, transients, or too high of a DC voltage. The Siglent front end is actually pretty impressive as far as what it'll handle. It'll take up to a 30 dBm signal and 50 volt DC on the input. You still got to watch out for transients sometimes. And a lot of radios, when you key them up, a lot of them have been known to transmit a spike the first few milliseconds when the radio is PTT'd, so be aware of that. Always better to start out with more attenuation between the radio and the spectrum analyzer, and then slowly remove that attenuation after you are convinced and assured that the radio isn't going to damage the spectrum analyzer. So what I've done here, it's pretty easy with the Flex because it is a software defined radio. I've gone ahead and set up the power output to be a nice low level. We're going to be using about 2 or 3 watts of RF. And the RF from the radio, what we're going to do, that signal is going to be coming into a 40 dB attenuator. This one here is rated for 50 watts, and it's good from DC to 8.5 gig, more than adequate for our needs here. The important thing is that it's going to be knocking the signal down 40 decibels. So if we start out with a couple of watt signal, by the time we knock it down 40 dB, we should be pretty safe coming into the spectrum analyzer front end. So what one very quick way to determine things like occupied bandwidth. Let's say you're on upper sideband mode and you want to know how wide your signal is. It's very easy to do. Set up the center frequency of the spectrum analyzer right at 14.2 megahertz. With the Siglent, it's beautiful. You can select a resolution bandwidth down to 10 hertz. The video bandwidth can also be set to 10 hertz, although a slightly higher bandwidth won't really hurt things either. But in this case I've got them both set to 10 hertz. And then I've got the span fairly narrow. We're going to be looking at about a 25 kilohertz slice based right at 14.2 megahertz. So you'll notice if I pick up the D104 and I start talking into it, we can see our envelope right there. All of the signals are appearing above 14.2, and that would represent the upper sideband of the signal. As you can see, it's pretty difficult to tell exactly how wide that signal is, since the sweep time is fairly slow and our modulation is constantly changing up and down. So a real-time display like this isn't very helpful. That's where the use of something like max hold comes in very handy. So we go ahead, what we're going to do is, you'll have to forgive me, trying to hold the camera and push buttons is not super easy. So I've got the spectrum analyzer now in a max hold mode, and I'm going to keep talking and pretend like I'm putting out a CQ. CQ 20 meters, CQ 20 meters, CQ 20 meters from WABYA, calling CQ 20 meters, CQ 20 meters from Whiskey 8 Bravo Yankee America, WABYA. Okay, so even something like this, which is very fast, kind of dirty if you will, you get a pretty good idea that all of our RF is starting at just above 14.2 megahertz, and then it goes higher in frequency because we're in upper sideband mode, and we can see that the peak amplitude of our audio is not very level. I've got a lot of lows in there. Looks like there's a predominant dip in the mid-range, and then the highs start coming up again. So it'd be nice if there was a better way to characterize the bandwidth. What we could do is set up a marker here at the low frequency end of the spectrum, set up another marker on the high end, and then measure the difference between those two markers, and that'll tell us effectively what the bandwidth of the transmitted signal was. There's a lot better ways of doing that though, and let me show you one that I like doing with a radio like this. What I've done, since this is a software defined radio, I'm using what's called virtual audio cables. It allows me to run software and couple the audio to and from that software to the radio without using physical wires. In this case, I went on the net and I found a very cool program put out by a firm called NCH Software. Really cool program. It lets you select all kinds of different audio frequencies and things like that. The one thing that I noticed that I really liked about it is it gives me the option of choosing, instead of single tones or double tones, things like that, it actually lets me pick something like a white noise source. And what white noise is, it's an audio signal that it's made up of random noise, and it covers a very wide frequency range, and theoretically it's all random noise, having approximately the same peak amplitude across the entire frequency spectrum where it's intended to be. So what I've done is I've taken that software and I'm going to set it up to generate a white noise signal, and it's going to go from several hertz up to probably 50 kilohertz, and I'm going to generate some white noise, and I'm going to inject it directly into the radio using the virtual audio cables. And what that does is it eliminates the microphone completely, me having to talk into the radio, the microphone characteristics, things like that, and it allows me to test the radio itself, which is really what we're after here. I want to know how the radio is performing. So let me go ahead and shut this off, and I'll set up the software to generate the white noise. We'll inject it into the radio, and we'll do the same test using that technique rather than what you saw here. Okay, so I've got the software set up now. You come up here to tone. You can see I've got white noise selected here, and if I hit play, the software now is generating, you can see our VU meter, if you will. It's generating the white noise, and it's being input through the virtual audio cables into the Flex radio via Power SDR here. I've gone ahead and reset the spectrum analyzer. I've cleared the display. We're going to hit max hold the way we did before, and I'll go ahead and put the radio in the transmit mode, and you can see instantly we get a really beautiful picture of what the occupied bandwidth of our transmitted signal is. If we go over here to the Flex, we can see there's our transmitted signal. The Flex display on Power SDR is much like a spectrum analyzer in itself. What I've done is I've set it up to ensure that I'm not overdriving the radio, and make sure the ALC is always below 0 dB. And you can see the spectra is very, very flat. Just like I mentioned earlier, the peak amplitude of the noise spectra should be constant across a very wide frequency range, and the noise theoretically should be random, although it's really not in this case, but it's very, very close to being random for our purposes anyway. It's more than random enough. I've also got the Flex set up. You can just make it out here. I've got the Flex set up so that the bandpass of the transmitted audio starts from 100 Hertz and goes up to 3 kilohertz. In other words, I don't want any audio below 100 Hertz, and I don't want any audio above 3 kilohertz to be transmitted. So theoretically, our bandpass audio that's being transmitted should be 2.9 kilohertz. So that's what the white noise looks like as it's being transmitted by the flex, and that's what the spectra looks like here on the spectrum analyzer. So let me go ahead and unkey the radio. We'll go ahead and put this in a view mode so that we're not sweeping anymore. And we'll set up a marker. And like right there, we could put a marker right there. And we press the delta button. And what we do is we slowly scan across. And we can come down right about there. And we can see that we get a bandwidth of about 2.966 kilohertz. So it's very, very close to the 2.9 kilohertz that I've specified in the Power SDR software. Now, usually the bandwidth is defined usually by the 3 dB point, so I'd have to come down 3 dB from the peak level here, and if I did that, this bandwidth would actually be less. It would be very close to 2.9 kilohertz. So this is one really quick and easy way to do this test. If you didn't have virtual audio cables or a way to directly inject the white noise from a software package like this, there's a lot of ways to kind of make to couple the signal. You could even take a speaker from your PC and hold it up next to your microphone while it's playing the white noise, and it would generate exactly the same plot here, only this time you'd be seeing the bandpass of your entire system. In other words, the microphone, the equalization of the microphone going through all of the wires and everything, interface of the radio, and then being transmitted, and then you'd get to see what the bandpass actually looks like. So if you have virtual audio cables, that's the cleanest way of doing it, to inject a signal like that, test signal. But if not, like I said, don't be afraid to experiment. You can take a speaker, like I use these loudspeakers here. These are amplified speakers. I really like them. I've got them connected to the PC, and because the Flex radio is software driven and all that, the audio from my radio comes out over these speakers. So you could take one of these speakers, move it close to the microphone, or take the microphone and move it up toward one of the speakers and just set it there so it's not moving around, and then play the white noise, put the radio in transmit mode, make sure there's no background noise going on, and put it in max hold mode, and you could generate a plot just like that that'll show what the bandpass is. So this is the manual way of doing it. Let me show you some more elaborate ways of doing it. The spectrum analyzer here, I was very fortunate when I purchased the spectrum analyzer. I also got the advanced measuring kit along with the tracking generator, and they've proven to be very, very useful. Well, what you do if you come over here and you hit the measure button, you'll notice we have quite a few different things that we can enable. We can have the spectrum analyzer measure the channel power. We can do the ACPR. That stands for adjacent channel power ratio. And in a nutshell, what that means, it's the amount of signal that's leaking into an adjacent channel, mainly via things like phase noise or intermodulation distortion, things like spectral regrowth and things like that. So it's an excellent way to characterize the transmitter's performance. It's become pretty much a standard. So channel power, ACPR, it actually has a button for occupied bandwidth. We'll be using that shortly. TPower, very, very interesting concept. It's kind of like a time domain power measurement. It lets us define a time interval that we want to measure the RF power of a signal. Of course, here we've got the third order intercept calculation that will take place. This test here, I remember doing it years ago. I'm originally from the aerospace industry as a lead tempest engineer, and we used to do this test when things got slow and helped out with some EMI work. And the test can be quite involving to be done properly. And what's amazing is how much power is packed into these new instruments and the software, like the advanced measuring kit, to give you the capability. Everything is done for you, and when we get to the part here where we actually do a measurement, it'll amaze you how fast and easy it is to set up and use. Also has a spectrum monitor, and that's another term for a waterfall display. And it actually, as you'll see, comes in pretty handy when you want to investigate the modulation of a signal like this. So this is how you do it if you don't have something like the advanced measurement kit installed. Now let's go ahead and quickly see if we can run through these. We'll enable these one by one and show you what happens when we use the same type of signal. We'll stick to the same frequency here on 20 meters, 14.2, and we'll see what we get. Okay, so we're ready to do our first measurement here. What I've done is I've changed our span to 20 kilohertz. We're still using narrow resolution bandwidth and video bandwidths, and we're still in a normal spectrum analyzer mode. If I go ahead and put the radio in transmit mode, you can see that's our familiar looking plot that we had earlier. So to enable the measurement, the advanced measurement kit, we go ahead and hit that button. Brings up our options. We go ahead and hit channel power, and right away you can see the spectrum analyzer changes its display, and it's showing the upper sideband there very nicely. And what's really cool is immediately it's performing some calculations for us. It's providing power spectral density, values of dBm per hertz, the integration bandwidth, which we can change by hitting the measurement setup button, and then it's giving the channel power. So in this case it's roughly 4, well, it's toggling between 4 and right around 4 dBm, maybe a little over. So how cool is that? It's giving us, what it's doing is, you can see along the top there's a red arrow, and that red arrow is graphically showing us what the channel width is, and in this case it's 20 kilohertz. So we've defined the channel width to be 20 kilohertz, and what the spectrum analyzer is doing for us is calculating the total power within that channel, and it's giving us a value pretty close to 4 dBm. So now let's see what happens. Any guesses what would happen if I were to take the span and reduce it to 10 kilohertz? If we take the same signal, but we take the channel bandwidth and we reduce it by a factor of 2 to 10 kilohertz. Are there any guesses what will happen to the channel power? We see values here going between 4 and 4.4 dBm, somewhere around there, but averaging right around 4 dBm. So let me go ahead and, since I can't hold this and operate the mouse at the same time, let me go ahead and shut this off, and I'll change the channel bandwidth to 10 kilohertz and we'll repeat the test. Okay, so now I've gone ahead and changed the span to 10 kilohertz. Let's go ahead and key up the radio. There's our familiar looking upper sideband signal, and as you can imagine, since we have the channel width, the modulation looks like we've zoomed in a little bit. Let's go ahead and enable the channel power. So there we go. It's the channel width now is defined by that red arrow, and it is 10 kilohertz. Notice this power spectral density, but look at that. The channel power has gone up by about 3 dB. So I'm sure a lot of you have already guessed that properly. Since we've halved the total amount of bandwidth that the signal is in, the power that's being integrated over that frequency has gone up by 3 dB. So it's kind of nice when the theory actually matches what we're seeing on the instrument in practice here. So this is one interesting tool, the channel power. You can define the channel to be any width that you want, and it'll provide some very useful data for you. The power spectral density, we can change the integration bandwidth, and it'll give you the channel power that you define here. Let's next move on to the ACPR, the adjacent channel power ratio. Okay, so I've gone ahead now and enabled the ACPR, and what pops up is a really cool looking graphical interface. You know, what it shows you are 3 channels. There's a primary channel here, and there's 2 adjacent channels. And what the spectrum analyzer is going to do with the advanced measuring kit, it's going to give us, first of all, lets us define what the main channel bandwidth is. In this case I set it up for 6 kilohertz. The adjacent channel bandwidths, I set them up to be 3 kilohertz. And then the spacing between them I set up to be 10 kilohertz. And that's from the centers. And then what it's going to do, it's going to give us the total integrated power within that channel for the main channel, for the left channel, and the right channel. It'll give us the absolute level of the signal. It'll also give us the value in dBc, which will be relative, of course, to the primary signal. So setting up these windows took just a few seconds. Again, we come over here to the measurement setup, and you can see right here we can define. I'll let this thing autofocus. Come on, I know you can do it. So there we go. Our center frequency is still 14.2. Our main channel width is 6 kilohertz. The adjacent channel is 3 kilohertz, and the spacing is 10 kilohertz, which is what we see here. So it's just that easy. You enter in the values, it'll graphically show you what those channels look like. Let's go ahead and key up the radio. Alright, there's our familiar looking upper sideband signal. Isn't that cool? And look at that. In real time, it's giving us data on what the integrated power is in each of the channels and their values in terms of the main carrier. In other words, the power that is in here in that channel relative to the fundamental. So very, very powerful and really super simple to set up. So let's move on to the next one now. Looks like that's going to be the occupied bandwidth. Alright, next on the list here is the occupied bandwidth option, and I've gone ahead and set it up for a 25 kilohertz span here. We're still using our 10 hertz bandwidths. You'll notice that the analyzer is providing us 3 pieces of information. It's saying that the percentage is going to be measured 99%. Well, what that basically means is that what we're going to do is we're going to be measuring the bandwidth that contains 99% of the total integrated power of the signal. In other words, we're going to be measuring 99% of that signal, of the intended signal. So we're getting just about the whole thing. It's also going to display the transmit frequency error, and then the occupied bandwidth. It'll actually do the calculation for us. This is probably one of the slickest little options that's on here, especially for us hams that want to know how wide our signal is. So notice right now it's sweeping, and we've got the same red line across the top here, arrow going from left to right. It's saying that the entire span here is the channel width. Because there's no signal present, it's saying, hey, you know, the occupied bandwidth here is, it's going to be the whole thing. It's going to be the whole window. So watch what happens when I go ahead and put the radio in transmit mode. There's our familiar looking white noise signal, upper sideband signal. We'll notice that it's saying the transmit frequency error is 1.55 kilohertz. And what that means is that it's giving us the difference in frequency between our center frequency, which is 14.2 megahertz, and the exact center of the transmitted bandwidth, if you will. The bandpass of the transmitted signal has this width. It automatically drew in that red line, and it's defining the bandpass, the transmitted bandwidth or bandpass, if you will. And so what it's doing is it's taken the exact center of that bandpass, and it's saying the difference in frequency between that and 14.2 is 1.55 kilohertz. And then it's saying the occupied bandwidth is 2.9 kilohertz, which is exactly what it should be. Remember originally when I set up the flex here to start transmitting at 100 hertz. Back off a little bit here. There we go. And you can see, in fact, there is actually no modulation right on that vertical division line, which is 14.2 meg. We're actually starting just a little bit to the right of that. So we're actually starting 100 hertz up higher, and then I have it stopping at 3 kilohertz. And so 3 kilohertz minus that 100 hertz starting frequency yields 2.9 kilohertz. So this automatically will determine the occupied bandwidth for you in a split second and display the results for you. So extremely powerful, and does everything for you rather than us doing it manually, worrying about setting up cursors and have we gone down far enough down the skirts. This goes and does it automatically. I'll have to look up to see whether it's defining the bandwidth by the 3 dB points or 6 dB points. It'd be kind of interesting to know. But anyway, it nailed the bandwidth exactly right at 2.9 kilohertz. So next, let's go on to the TPower. T stands for time, and this is a very, very interesting measurement capability that they've added. And again, it really represents the time domain power. It's going to calculate the power of our signal based on time parameters that we define. So let's move on to that. Alright, so I've gone ahead and selected TPower. I'm going to keep the same span as before. I haven't changed anything on the analyzer. I really could have kept rolling the video here and just selected TPower here. Let me go ahead and key up the radio again, and there we see our very familiar upper sideband signal. Modulation in this case is the white noise source. Now what you see in the TPower measurement, way over on the left side, we see a pair of vertical red lines. There's a little arrow between them. Those are time markers. And it's saying right now that the start line is 0 seconds and the stop line is 20 milliseconds. And it's giving us the integrated power over, in this case, 20 milliseconds, and it's saying the value is roughly a minus 100, 102 dBm. Let's go ahead and move the cursors to where our modulation is. So we come over here, again, real easy. We define the start line, and all I'm going to do is take the thumb wheel here, let me start with the stop line. There we go. So you can see as I'm moving the thumb wheel, the end line is moving closer and closer. And what I want to do in this case, since I'm interested in the width of my modulation, I'm just going to go ahead and rough that in and put it to where I think the modulation is ending. And we'll say right about there. And then I'll go ahead and hit the start line, and I'll move it over. There we go. So what it's letting me do is define the start and stop times of where the modulation is occurring. So in this case we're going to be taking a measurement from 1.19 seconds to 1.46 seconds. That's where that modulation is occurring, and it's giving us the integrated power in that time frame to be minus 37 roughly and a half dBm. So again, very, very powerful tool that's available at your fingertips here. In just a matter of seconds you can define it any which way you want. I just find it fascinating how much power they've put into these new instruments. It's just fascinating to have it all available and with such accuracy, and to be able to set it up so quick. It just is really cool. Alright, so let's go back to measurement. Let's take a look at the third order intercept. Let's see what kind of trouble we can get into there. Alright, so I've gone ahead and put the analyzer in the third order intercept mode, test mode, and I've changed the span to 20 kilohertz versus 25 so that we can zoom in a little bit. I've also changed the software a little bit here. Rather than a white noise source, I'm going to have it generate two test tones, one of them at 1 kilohertz, one at 1500 hertz, 1.5 kilohertz. And we'll have the transmitter transmit both of those tones simultaneously. So let's go ahead and put the radio in transmit mode. This calculation is very, very intensive. It seems to draw on the computing power of the spectrum analyzer quite heavily. I notice there's a little bit of time lag. You want to take your time when you're pushing buttons to change any of the variables. Otherwise you can lock up the analyzer. So what's kind of cool is those are our two main tones, and of course we've generated all kinds of intermodulation distortion products, and the analyzer is all too happy but to calculate what they are for us. So it'll go ahead and give us a lower bass frequency, upper bass, the lower third order intercept, and the upper gives you the frequencies for them, gives you an absolute value, and it'll give you the value in terms of dBc and then the intercept value itself. So not real stellar, to be honest. Really could be a lot better, but it is what it is. Radio is quite old, been discontinued quite a while. Anyway, it just shows you how fast, how easy it is to perform the measurement with the advanced measurement kit. It automatically finds these points for you and then does the measurements and calculations for you. But again, take your time and don't rush the machine. It takes sometimes 5 or 10 seconds for it to react. But very, very cool. To do this calculation, to do the measurements manually, was quite labor intensive, and that if you're not used to doing it, definitely you're prone to making mistakes and errors, things like that. So this is a very cool feature to have. Alright, let's move on to the final thing, which is the spectrum monitor, which is really another way of calling it a waterfall, which can be very handy also. Okay, here's our final test. We're using the waterfall display, or spectrum monitor as it's called in the advanced measurement kit. I'm using the same two tones that we used before. I've changed the span to 10 kilohertz so that we're looking more right at the center of the modulation and the distortion products. The top part here is when I had a span of 20 kilohertz, and you can see really cool display of what the waterfall looks like. And then starting from the bottom, slowly making their way up, is the new waterfall with a span of 10 kilohertz. Of course, the color represents the intensity of the signal, red being the most highest value signals and blue being the lowest. And that corresponds to the way we've got the y-axis set up. We can change that to anything that we want, so we can actually make these colors suit our needs. But you can see it's very, very handy. You get a pretty good idea of the spectral purity. Sometimes it's hard when you're looking at a display like this. It's changing in real time. It's kind of hard to gauge what the purity is, what the amplitude of some of the signals are, the background noise, things like that. To be able to see it in a waterfall like this, it's pretty interesting. You can see that the background noise doesn't exist at all back on these lower frequencies or way up high, but within the range of the two primary frequencies. And the first three products here, we see that there is quite a bit of phase noise or something going on. So comes in very handy. And again, just took a few seconds to set up. Alright, let me go ahead and unkey the radio. So I hope you found this useful, and if you have any comments or questions, don't hesitate to ask me or email me. My email address is oknqrz.com, or if you want, it's just wabya@mchsi.com. So again, hope you found it useful and helpful, and I wish you a very good weekend. 73.